Okay, so last time, before the Quizlet, what were we talking about? Yep, talking about spheres, particle on spheres. We came up with these special functions. What were they called? Gave you a little sheet with them on it.
It starts with L.
We need L and ML.
Oh, then
but
it's not.
They're called the spherical harmonic functions. So we talked about those. We kind of drew some pictures of what they looked like. I had a cool what I thought was a cool animation up, where they were changing signs back and forth, and to see how complex they were and how they're actually related to the SP, D, F, and other orbitals that we'll see in a little bit. There are some other aspects to particle on a sphere that I want to highlight. We didn't talk about the energy of the system. The other thing that we didn't discuss was space quantization, which we'll get to in a little bit, which is a weird effect. And then the rest of today, we'll talk about how to integrate spherical polar coordinates, and we'll set up everything to move to where we can vary R in our system, because we've kept that fixed because it looks a little difficult. Okay, so let's talk about the energy. For a particle on a sphere. Okay, let's go back to the Schrodinger equation. We ended up at this point. Which looks a little bit different than our generic Schrodinger equation. What's this I thing? Yep. And then what was this lambda thing? Yeah, which two? Not R, yeah. Theta and phi, so it's basically like the gradient, except we're not varying R. We've taken out all the R stuff. Okay. We changed these wave functions to be something else. Those are the spherical harmonics. What symbol do we give the spherical harmonics? Yep, Y. And then what do we need to indicate for Y? What two quantum numbers? Yep, L, and what else? Yep. And what is the only stuff that Y depended on? Yep. Oops. So you have to select an L and an ML value that will tell you what the spherical harmonic function looks like. Okay, something I don't think that we justified, but we stated was if you applied that lambda squared to this system, there had to be a relationship that was observed. You had to get this out. Negative L plus 1 theta B. So we know those two things are true. They have to be true based upon the restrictions that come about from the spherical harmonic functions. I said there's something about Lagrange polynomials. This is a mathematical relationship that falls out that I don't want to justify because it takes too much time. Everybody's okay with that, right? Okay, but we're going to use this. So now, how will these two equations, we'll sub this one into that guy, what are we going to get as a result? Negative h bar squared. What else? Uh-huh. Yeah. And what's that all equal to? Yeah. We want to get an expression for the energy though, so what can we do? Yeah. We can divide through by y, we end up with this. So what are we going to get for energy? Oh, honestly, I should have put ml, sorry. ml is going to be equal to what? Okay, simplify that further. What can we pull out of here? Yeah, get a negative out of there. So you end up with L times L plus 1 h bar squared over 2y. So what do you have to know the energy of this system? Yeah, you just have to know L. You actually have to go through any of these crazy derivatives or other things to figure this out? No, you don't have to. All you really have to know is L. Okay, what do you know about L? Yep. What are the possible values it could have? Yeah, ... to n minus 1. So you can only have these values. What does that mean? Or what does this show in comparison to classical physics? Yeah, it's quantized. So this means the energy is quantized. Okay. That's not too surprising because we knew we were dealing with a quantum system. We've seen that a handful of other times. But what we're going to show next is there's actually something called space quantization, where if you're thinking about different values of angular momentum, so you've seen it where somebody has a bucket and they swash around like that and the water stays in the bucket, right? Yes? Okay. Now, if you think about it, that means the atom, or excuse me, this quantum system only has different specific ways it can do that. You couldn't have like your arm go out in different angles. It's either got to be here, here, or here. Which again is weird, meaning it can only be in that portion of space. So let's talk about that. Or at least the angular momentum can only have those values, which is very, very different from what we observe. This is often called space quantization. So again, what controls your energy? Yep. And how do we calculate the value of L? For an atom, we use the principal quantum number, but for this system, let's say we don't know L, what do we have to know? Yeah, if we know M sub L, then we could have a possibility of L's. So there are only so many values of M sub L for a given value of L. How many, if you had to come up with a generic relationship or a formula to calculate the number of M sub L values, what would it be? Yeah. Okay. And what M sub L was the value of the angular momentum with respect to the z-axis. We set it arbitrary to the z-axis. You can pick any one, but we're going to go with z. So this means that M sub L, where what that was the angular momentum, about the z-axis can only have certain values. Now that's kind of strange in itself, because what that means is the particle traveling around on that sphere can only have so many possible orientations. The particle can only have so many orientations. Meaning the space itself is quantized that this particle can travel in. So let's try to look at a visual representation of this. Let's see what we mean here. Let's look at an example of L is equal to 2. What are the possible values of M sub L that we could have? Zero. Yep, for how many different values? Yep, so how many different orientations? Yep. So 5 different orientations. Let's try to draw those. Okay. This is our z-axis. We're going to draw all the possible paths of having an M sub L equal to 0, -1, +1, -2, +2. We're going to show the path that could possibly have with a blue circle. And we're going to show the m sub l value with a red vector. Okay. ml equal to 0, that means it is perpendicular to the z-axis. So where should I draw my red arrow? If it's perpendicular to the z-axis. Yeah. So this is an ml value is equal to 0. Have you guys learned about the right-hand rule or the left-hand rule? Okay. So it's a cross product. If the vector is pointing this way from the angular momentum, which way is the particle traveling? Yeah, so it's curling in and out of the board, but it's going along the z-axis. So I'm going to draw it kind of at a curved angle, but it's going zoop, like that. And it's meant to be in the plane of the z-axis. Okay, an m sub l value of 1. How would that look? So first thing is will it be pointing up or down? That's positive 1. It'll be pointing up. It'll be at an angle. That. If I had m sub l equal to -1, which way would it point? Yep, point down, but approximately the same angle just reflected. Okay, right-hand rule, it's going to be rotating off that 90 degrees. It'll be rotating around that way. This guy, it's going to be spinning the other way. Oops, I want to show it like that. Okay, what about an L value equal to 2? You doing it? Yeah, it's hard to show. What's going to happen to this angle? So we went from here to here. If I increase it to L is equal to 2, it's going to go up a little bit more. In this case, it'll angle down a little bit more. In this case, want it to kind of travel like this. It's hard to draw. And in this case, okay. What it means is as long as we draw it simply like this, simply. But what we're really saying is any point on here, on this cone, all points to that vector. So it gives you a variety of different values it could possibly have, but the ML value has to all point to that direction. Okay? So there's a range of different values it could possibly have. Does that explanation make some sense? This is one of the most difficult concepts around because you really have to understand angular momentum and how the right-hand rule works or the left-hand rule if you're Russian. But looking at this, what it's trying to basically say is this ML value has a given value, it has to be conserved. And that is very different than classical physics where something can rotate and turn at any point it wants to be. Here, it has to be at specific values. Does that at least make sense? Or at least is understandable? Okay. These rotational levels, since there's a specific value it has to take, how do you think experimentally we probe this stuff? Or whenever we talk about probing these things, what do you guys use to detect quantization in the lab? Can you name any instruments? Yeah, NMR. Nuclei spins, other things. IR, yep. That's for vibration or the harmonic oscillator. This has to deal with rotational spectroscopy, which we don't use a ton. There's some people who find it very useful. We don't have one. But chances are, if you're like me, you use this to your advantage every single day. How many people cook with a microwave? I use a microwave every day. Next to indoor plumbing, that's the best thing ever. Does anybody know how it works? Okay. It works through quantization. You hit a wavelength. What molecule are you trying to rotate? It's water. So you're rotating water molecules, and it's actually creating friction, giving off energy that way. And the way it works is through this space quantization, which is pretty cool. There are some people who refuse to use the microwave. I'm thinking of like my great-grandmother. She had one in her basement because she was afraid of the radiation. You don't have to be afraid of the radiation. It can't permeate your skin. The other thing is I hear comments of, well, it changes the chemical structure, which I think is the dumbest comment I've ever heard, because that's what cooking does, is it changes the chemical structure. So I don't know. The way it works, though, is through that. Space quantization does work, too, through NMR when we're talking about the nuclei having specific values, too. Okay, so I just wanted to highlight how that's different, how it's kind of strange, and we're going to see it crop back up again for atoms. Are there any questions about this? Oh. Okay, it's a difficult concept. Try to understand it. It took me a long time to get there. And really, you kind of have to go back to understanding what are these vectors and what do those things mean if you want to get a true understanding of it. You don't need to know it all the way. Just know that space is quantized when you're talking about things that can move in this direction and along that direction. Okay, the next thing I want to talk about is more of a mathematical topic. We haven't done this yet, but I want to talk about how do we actually integrate spherical polar coordinates. We're going to go through an example where we look at a spherical harmonic function. We want to know the probability, or we want to normalize something. How do we actually mathematically go through that? Let's talk about the integration. Spherical polar coordinates. It's probably been a while since you've done a triple integral. Let's go through, yeah, no, exciting, hooray. This one will only be, we'll start with a triple integral and we'll make our way to a double integral. Then when we have to do a triple, we'll go back to that. Okay. So my first question is what is d tau? For a 3D system. Yes. Could be dx, dy, dz. And we've used that in the past for particle in a 3D box, right? However, we don't have the luxury of using that anymore. So my next question is what is d tau? In polar coordinates. You look back at it, we just kind of spit this out on a page. But what things do you think we're going to have to integrate over? R, theta, phi. And we also have to introduce r squared sine theta, dr, d theta, phi. All right. Should we draw a picture to describe what r, theta, and phi are again, or do you feel like you guys got it? Anybody want a picture? I will. No? We're good? Okay. So, one integrates. We got to think about the integration limits that we have. So for r, what did r describe again? Yep, the radius. Where would we start then? Yep. So what would the middle's value be? The origin. Yep. We're going from 0 to what? Yeah. We just go from 0 to r. We haven't really done that yet. We will do that soon because we've kept r fixed in all of our cases, right? Okay, phi. Yep. So that completes a circle kind of along the equator of the sphere. Theta. What are we going to go to there? Not the exact same thing. If we do that, we'll end up at a situation where we double count because we've already included some of that information in phi. Yeah, we want to go from 0 to pi. If you decided to swap these around, you could. But by convention, we generally just do this. Otherwise, you're going to run into a situation where you're double counting both halves of the sphere. Okay. Then to integrates. Some function that depends on r, theta, and phi. How many integral signs are we going to need? How do you know? Yep, 3 variables, 3 integral signs. First one, what are we going to do? Yep. Second one. Yep. And what's that for? Yep. Last one. 0 to what? And what's that one for? Yep. Okay. Then we throw in our function. What else do I need to throw in here? Yep, dr, d theta, d phi. What else do I need? Yeah. So we got to tack that other stuff in. A question I get sometimes is does the order matter? It shouldn't. We deal with Hermitian functions, which we should be okay to split a lot of stuff up. We could show through separation of variables, hey, everything's okay. You'd have to prove that in a mathematical sense, but we should be okay with everything we'll see in this class. Okay. However, we're talking about spherical harmonic functions, so what thing is fixed? Yep. R is fixed. And F depends only on theta and phi. Then we can ditch the R stuff. We have theta from 0 to pi, phi from 0 to 2 pi, theta, phi. What else do we got to tack in here? Yep. The R squared can actually sort of get incorporated into normalization functions and other stuff. So we're going to express it like this. And what d's do I need? Yep. Okay. So let's try to look at a situation that we can prove and utilize this, because you're going to see it crop up every once in a while. And then after that, we'll be done for the day, so you can drive as far north to see the sun get blotted out of the sky. Am I okay to erase this? Yeah. See it get dark in the middle of the day. That's how I described it to my daughter. She kept on calling it eclipse, like eclipse party, and she's like, I need a hair clip today. And I'm like, that's not what's happening. And she's like, Dad, it's a hair clip. Like, we're having a hair clip party. Get the hair clips. Yeah, I think so too. Well, I'm sure she'll have like 4 hair clips in her hair. And I like drew, we played with models and flashlights to explain what's going on. And she's like, yeah, that's cool, but I want to wear a hair clip. So we'll see how it goes. All right, we're going to take a spherical harmonic function. We're going to do y11. So confirm y11, oops, 1 comma 1 is normalized. Okay, so what are we really talking about doing here? Or how could we show that something is normalized? Or what does normalization mean again, in like a generic sense? Yep. 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 Yeah, we'll leave it be tau because we're lazy. That works. I'm lazy, not you. And what are my integration limits in this case? Yeah. Well, we can apply them a little. Yeah, we technically need to, because we put these y's here. Yeah, we should be a little more formal. I'm going to leave it off for now, though. But yeah, we should have 2. And as soon as we switch to y, we should go from 0 to pi and 0 to 2 pi for theta and phi. And yeah, we should have changed that too. All right, anyways. We're going to have to do that. Show it's equal to 1. What do we need first, though? We would need a normalization constant. We'd have to know what y looks like. Do you know what y looks like? Where are you going to get that from? Yeah, table. Okay, that table includes ones that are already normalized. Score! You don't have to calculate or figure out what the normalization constant is because it's already in there. The other benefit is you already know the answer. What's the answer going to be? Yeah, well, it is normalized, and its value is equal to 1, so we just got to show that. Okay, but what is the actual form or the equation for y11? Yep.
Negative 3 over 8 pi is the limit. And then it's sine of theta, and then there's e plus I times b.
Yep. That's it. It's nice because these are easily separable. Okay. So we got that as our wave function. Now, let's write our actual integral. We got 1. We need 2 integral signs. What are they? And what's that one for? Yep. The other one? Yep, and which one's that for? Yep. Okay. Now we need the complex conjugate of y, or that spherical harmonic function. What's going to change in here? Yeah. Everything else stays, though. E to the negative I phi times. Now we just need the regular function. We can rewrite that out. Okay, what next? Yep. Okay. Can you simplify this thing for me? Yep. So pull that out, 3 pi like that. What else would you do? So we're taking care of this. How many signs are we going to have?
Oh, there's 3 of them.
Yep. 1, 2, 3. What do you notice about those? They're all the same. So what could we do with this integral? Sine to the what? Yep. We can break that out, right? Times. Now we got to worry about the phi terms. Yep. we got these things. It's e to the 0. So that's just d phi. So what's that one going to be? Yep, it's just going to be whatever the value of phi is, and it will end up being what? Yeah. So now we got 3 times 2 pi over 8 pi that. Pi's are going to cancel. We get 6. What would you do next? Integral table. If you look up the integral table, there is one. I'm not going to write that one down. But when you evaluate it all out, what you get for 2/3 plus 2/3. Like that. Okay, let's simplify this thing. 3 over 4, what is it in the brackets? 4/3. Hey, 3/4 times 4/3, what's that going to be? Yeah. Woo, it works. Okay. So what I would suggest is take some of those spherical harmonic functions, prove that they're normalized, so you can just refresh yourself on how to do these double integrals and things. Is anyone confused or not sure of any of the steps right now? The beauty is this, the phi portions of things generally tend to cancel out and you just get 2 pi, which is great. But when they're all combined together, that's where it gets tough. So, what is it? Like, well, if you look at most of these guys, you don't really have phi sticking out anywhere. I wouldn't want to do anything where cosine and sine touch each other, though. Those are usually bad. All right, no other questions?